All right, stat students, so we are continuing where we left off on the binomial random variables, and good news, I have my MobiPad back now, so the writing should be a little bit better. We'll see. I kind of got used to not using it, but I'll try to implement it this week in these lessons. So we're going to continue on binomial random variables. Let's go ahead and get into it. Okay, so in your notes, you should have this written from prior lessons. We have the counting coin flips for the this random variable, okay? So we're counting the number of heads in 4 flips. So what our goal is going to be right now is we want to make the probability distribution for this. Before we do that, though, we're going to go ahead and write down a couple things. Okay, so we're going to talk a little bit more about binomial random variables. We need to write down some definitions here. So a binomial random variable in regular terms, what we're trying to do with these is we're trying to find the likelihood of a number of successes within a number of trials. So we're going to be interested in what's the probability that I flip and get 3 heads in a row. Okay, of course, we can do that pretty easily right now, but we'll raise this to, like, let's say we do 10 flips of a coin, and we'll put it in different scenarios. Okay, so let's go ahead and write this down. Right here it says the count x of successes in a binomial setting is a binomial random variable. The probability distribution x, which is what we're about to create, is a binomial distribution with parameters n and p. N is the number of trials in the chance process. P is the probability of success on any one trial. So these are going to be very important parts for when we get into calculation, which is going to happen in this lesson. Okay, so I'll pause and let you write this. Okay, so let's go back to our notes, and we are going to create the probability distribution. So what I'm going to have you do is I'm going to have you draw a let's make a table. Okay, and in this table, for like any random variable, we have x and we have p of x. Okay, and we're going to say x is equal to number of heads. And we know that we're flipping this 4 times. Well, let's list out all the possible counts that I could get. Well, first off, we could get 0 heads, right? Then we could get 1 head, 2 heads, 3 heads, and 4 heads. And we couldn't get any more than that. So I'm going to reduce my table a little bit. Now, what we want to do is we want to find these probabilities. So first off, what's the total sample space? Because that's what this tree diagram shows. It's all the possibilities. So what we're doing is we're counting all the paths. So we'll see we have 1 path, 2 paths, 3. What we're really doing is counting the heads and tails on this last column here. You'll notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 16 of those. Okay? 16 of those. So we're going to, if I can get this to work, it's supposed to be working. Okay, whoops. This is kind of not responding right now. I think we're getting it. Okay, so we know that all of these should have a 16 on the bottom. So in your notes, go ahead and write that in. Okay, so now we want to make these probabilities, and this is going to feel a lot like last chapter, where we're figuring out these probabilities. We're doing, we need to know what is the number of outcomes that produce 0 heads. Well, there's just one. It's this bottom path right here. So we know this needs to be a 1. Well, how many just have 1, right? Well, what's the only path that has just 1? Well, there's actually a couple of those. Instead of us actually going through and counting them, we can do it. Let's start here. Go all the way down this path. Here's a path that only produces 1 head, right? Here, tail, here's a head, tail, tail. So this one has 1 head, right? Then we can go again. There won't be another one here. Head, tail, tail. I might have missed one. Let's see. Tail. Oh, I missed this one right here. One head. And then head, tail, tail, tail. So this one here. So there should be 4 paths. Now let's talk about this. If this was 10 coin flips, this would be a very annoying process to do. Okay? A very annoying process. So we need a faster way to do this for when we get to, when we're trying to figure out how many combinations actually exist. So what we're getting into is something called combinatorics. And we have a formula that's going to help us figure this out. Okay, so I'm going to copy that in here. Okay, you know what, as a matter of fact, we're going to go ahead and look at this slide here. This is what we need. We specifically need this section right here. That's I'm moving the highlight around. This is what we need, but I'm going to have you go ahead and write this. So we're going to be calculating not only probabilities, but we're going to be finding the counts for an exact desired outcomes. Okay, so first off, we can generalize this for any setting in which we are interested in K successes in N trials. That is, so K is going to represent successes. So let's actually underline that when we're writing it, and N is the number of trials. Okay, so that might be something that we need to write down. I'm going to go ahead and copy this into our notes over here, as long as it allows me to do so. It did not allow me to do so. Hold on. There we go. Paste it. Good. So this is what we need. All right. So let me go ahead and pause it. I'll go back to this real quick, and we'll get this written. Okay. So let's explain how this works. Over here in your notes, we're going to be using this. So N is the number of trials, and then K is the number of successes. So this does not take into account probabilities at all. This is just basically counting within the mapping of your sample space that we have here, this sequence. It's counting, it knows how many should be there, and it's going to say, okay, you're going to have this many amount of successes within this many trials. Okay, because it's a binary situation, a binomial distribution will always end up having a tree diagram just like this. Now the probabilities will be different, but it will be able to map out the combinations the same way every single time. So it's a pretty cool formula here. Now we have a new symbol that's called a factorial. You may have seen this before. Most of the time it's only used in a statistics setting, so it may be unlikely actually that you've seen this. Let me go ahead and pull up a definition for us. Factorial function says to multiply all whole numbers from our chosen number down to 1. Okay, so here's an example. 4 factorial is 4 times 3 times 2 times 1. Okay, so we're gonna do 2 for this. We're gonna end up getting our calculator involved, but I just want to show what this is actually doing. So if I wanted to say, and we'll write it like this: 4, 2. This is N, K. This is how you know that you're doing combinatorics. 4, 2 is equal to 4 factorial over 2 factorial times 4 minus 2 factorial. Again, what it's doing is it's mapping out in our binomial sample space there in that setting, it knows, okay, there's going to be 4 rows of this tree diagram of these binomial choices. I'm looking for 2 of the successes within that. Okay, that's what this is actually saying. What this looks like numerically, if we were going to do it slowly and by hand, because we're going to get our calculator involved in this for sure. If I can get my this MobiPad involved. This MobiPad is not doing it right now. No. All right, I'm gonna pause. I'll get this figured out. Hold on. Don't know what happened with it, but so we'll just go on without it. I'm just gonna type this in here. So this is 4 times, I'll use an X, times 3 times 2 times 1. That goes up top. Down below, this is 2 times 1. And in parentheses, we're going to have 4 minus 2, which is 2 factorial. So this is 2 times 1. So this will go right next to it. And this will give us the number of combinations that result in a 2. Now let's look at this on our calculator. Let me clear all this. So what you'd want to do on your calculator on the Inspire is you're going to make a fraction. So you hit Control Divide to make that fraction. You're going to put the number of successes, which we know is 4. And then let's talk about where the factorial button is. You'll see right next to the letter G right here, I've highlighted it red, you'll get a pop-up. This is the factorial, and we want that. Then we go down, and we're going to do 2 factorial times 4 minus 2, close the parentheses, and we want another factorial. Hit enter, and this is going to give us the number of combinations for this. So we're going to get 6. So we're going to write in here 6. Okay, and now we can quickly do this for all the rest, because watch, all we need to do is go up and copy. And all you're actually changing to get the rest of these combinations is this number of successes, K. This is now a 1, because I want to find number of successes for getting exactly 1 head. I hit enter. That's 4. Okay, there we go. Next, you go up, we want 3. 3. Hit enter. That gives us 4. Again, so you'll notice that we're going to have some symmetry here in these probabilities. Let's do this. We didn't actually check. Let's check 0. Let's see what happens when we put in 0 here. And you might be wondering, well, what is 0 factorial? How does that work? Well, let's go ahead and hit enter. We get 1 for this, so we know this is a 1 like we had predicted. But let's just type in 0 factorial. What is 0 factorial? Well, it's 1. Now, initially, that's kind of confusing. And understandably so, but the way that factorials are actually defined mathematically, because I gave you the rule here, okay, shorthand factorial. Let's see if this, I've got a website here. What about 0? So 0 factorial is interesting, is generally agreed that 0 factorial is equal to 1. But this diagram here sort of is showing why. But I have another website here that actually goes through like a mathematical proof. I'll pause the video and link that in there for your own interest. But in general, just remember that 0 factorial is 1, okay? So that's what's causing that to happen. This is 4 factorial. This actually ends up being, when it's all said and done, 4 factorial over 4 factorial. Right there, which is 1, as we know. That's what this ends up being. So we have 1. How many combinations result in 4 heads? Well, we should know that there's only 1 combination that makes that work, but we're just going to confirm it using this formula. And again, we're going to get 4 factorial over 4 factorial, so it's a 1. Now, remember how I had shown in the last video that 50-50 probabilities create a normal distribution? That was something that we saw with that Galton board. I've actually taken this distribution, I put it in here. Right, here's all the probabilities. that we just found. They're simplified a little bit. And then I graphed it. So look what we get here, a nice uniform, not uniform, symmetric normal distribution is what's occurring here, okay? That's what's happening with this binomial distribution. So what happens when we increase this, okay? Let's do this scenario. So we're going to say 10 flips x equals, actually let's make it y equals number of heads. Okay? So we're going to rewrite this, x and p of x okay, and we're going to list out all the values. So this will be 0. It goes from 0 to 10. 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let's go ahead and fill this in. Right here, actually, I'm going to go this direction. Okay, so we're going to get our probabilities. Now, remember how last time on the denominators, we knew the number of combinations. Now, since I'm not going to draw one of these tree diagrams for 10, because it's just going to be too many, we have to figure out a way to know, well, how many total how many options are there? So here is how we do that. So we're going to say, we're gonna add this to our notes here. We'll put this here. So write this down. Number of total outcomes for a binary or binomial distribution, or I'll say setting, is, and I'm going to write this, 2 to the n. Okay? 2 to the n. And this, for those that understand how computers work, this is actually going to be kind of an enlightening situation here, maybe. Maybe it will be. But let's make sense of this. So if I do 2 to the, if we had 4, n is the number of trials, 2 to the 4, we had 16 trials on this one, right? So how many are we going to have for 10 trials? And we need to make sure we put that n equals number of trials. I believe we've already covered our bases on that. We should know that n is number of trials when we're talking about this. So how many trials will there be? Well, there'll be 2 to the 10, which is going to be 1,024. And I can guarantee that none of you would want to write or to draw that 1,024 paths and have to do all the counting within that. That would just not be very fun, would it? So 1,024 of those. And I'm going to make sure, I'm going to draw all these, and we're going to, in every single slot, let's go ahead and write that down, 1,024. I'm going to do some copying and pasting here. So I'll get all mine set up. Okay, so we have all of these listed out. Now we just need to find the number of combinations. So we got to go back up and do our binomial coefficient, the combinatorics, inside of these 1,024 possibilities. How many of them result in no heads. Well, we don't actually even need to do that because it's always going to be 1. And on the ends of this, it's always going to be 1. We could actually prove it. Let's go ahead and write up our formula we want. It's going to be we're using this factorial formula. So we have 10 trials. So we factorial that. We want 0 successes. So 0 factorial. Parentheses 10 minus 0 factorial. Using our formula, we hit enter and we get 1. So now we're just going to repeat this process. All we're doing is going through and we're pressing and we're just changing all the numbers within here. So this is 10. Let's do the next one. 2. Hit enter. 45. Now, I've already thought, man, this is kind of repetitive. And you know, anytime there's a repetitive task, we can always find a way to have a computer do our work for you. So let's actually call this N for number of trial. Actually, no, let's call this K for number of successes, and we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We're going to have the computer auto do all of this for us because I'm already bored of doing this. Even though it's pretty easy, the computer's already copying and pasting. We can do this faster. So K is the number of desired successes, and we're going to say number, right? How many trials produce that? So we're going to put an equal sign in here. I'm going to make my fraction. We know that there's 10 factorial trials. Over, we want K factorial, right? Which we already have K defined. Times 10 minus K, close that, factorial. And K is column reference. That didn't work. All right, I think we need variable reference is what they want. So variable references. There it is. All right, perfect. And so look, we already did, oh, and I forgot 0, but we already know what 0 is. So 10, 45, 120, 210, 252. Okay. 210. So it's just going to go back down. 210, 120, and then, yeah, that's 120, 45, 10. So there's our binomial distribution. And let's do something else. Let's call it P of X, right? And this actually could have been X here that I could have put. PXK, I'll call it. And we can say, okay, this is going to be number divided by 1024. So there's all the probabilities simplified on here. I did forget to, I need to put 0 in here. There we go, got it. So now I'm going to make the graph of this distribution. You don't have to do all this with me. I'm sort of doing this to entertain myself. But I just want to show, I want to continue talking about the point that this is going to be, hold on. This is going to also be a normal distribution or close to it, right? There it is. So there it is, that normal distribution. This is so close to the Galton board. The Galton board, if we had actually put 12 trials, remember that's how many trials we said we had, we would get it, okay? And we could, with this formula I have, we could just add this on here. I would have to go back and change this to 12, but let's actually do that. Let's get the Galton board distribution. 11, and we want 12, and then I need to go back and change these numbers to 12, 12, overwrite, yep. And then instead of, let's change this to 2 to the 12, because that's our combinations. Yep, there's our new probabilities all right there. Let's make oh, actually we already have the page. So we go back to this page. Here's the Galton board right here. That's what those beads were doing on there. So this is our idea of how we're creating these binomial distributions, okay? Let's talk about this number 1024. Those that are into computer science, you'll notice that this is the size of 1024 bits make up a kilobyte, right? 1024 kilobytes makes up a megabyte. 1024 megabytes makes up a gigabyte of data, okay? 1024 gigabytes makes up a terabyte, which is what most of our storage is these days. So if you've ever heard the term terabyte and gigabyte, megabytes, this is where that's coming from. And computers use binary, right? That's how they communicate, zeros and ones. They choose yes or no, it's success or failure. And this is where we can sort of draw that connection between them. So if any of you are getting into computer science one day, these ideas come into play. They absolutely do. Okay. All right, we're gonna do. We're gonna answer a couple questions. We can actually find the probabilities of these by using this formula here. We could have found, so we have the number of arrangements times the p to the k times 1 minus p to the n minus k. This is our formula for finding exact probabilities. All right. And for AP students, this is going to be more important for you guys. Dual credit, we are going to rely pretty much entirely on the calculator to do this for us. But if I had asked you, so we're going to write down some calculator steps here. We're actually going to get rid of, actually, no. Okay. So we only want the Inspire instructions. So if we want to calculate binomial probabilities, so if it says what's the probability of getting, what is the probability of getting exactly 3 heads in 10 trials, let's say, okay? We have what's called Binomial Pdf and Binomial CDF. And I want you to write down these parts here. So we're going to actually put all of this into our notes right here. And so we have, to find this, you're going to press menu 5, and then you're going to scroll. It's all the way down. You have a Binomial Pdf, which is for exact probabilities, but Binomial CDF is for a range of probabilities. And you're going to see all of these lingos here, all of these at least, and this is where it can get confusing for some students, but all of these are going to be what you use to help you calculate this. So we're going to actually go ahead and practice these, and I'm going to give 2 examples for this. Okay. So let's go ahead and write this up in our notes. I want to find, so example, what is the probability of flipping a coin 10 times and then we'll do 1 getting exactly 3 heads. Well, we already found that probability, right? We already found this probability here, 120 out of 1024. And if we do the calculation on that, 210 120 divided by 1024, we get 0.1171. But I want to show this new method that we can use instead of going through all of this work, which, this is quite a bit of work. I just wanted to show it to you so you understand the composition of a binomial distribution. But on ACT, on dual credit test, that's a lot. That takes a lot of time, and we're not really interested in spending a ton of time making this. We're going to have the calculator work through the problem for us, okay? So go back to your calculator page, and we have these new this method here to finding it. So this is for exactly, go find Binomial Pdf. So it's menu 55, so menu 55. And then here's where we had normal CDF. So you remember normal CDF and inverse norm. We don't want those. We're going to go down until we find Binomial PDF. We choose PDF when it says exact amount of trials. Okay, and we'll talk about CDF in a second, but go ahead and hit that. And it's pretty straightforward what we need to type in. The number of trials. And so let's go back over here. N equals, and then K equals. That's what's going in, or excuse me, P. We need probability. We'll actually need all of these. We need P, probability of success, and then K, which is the number of successes you want. So what is the number of trials? Well, it's 10. What's the probability? 0.5. And then what is the number of successes we want? We want 3 successes. That's all we have to do. It should equal this value up here. And let's go ahead and write this actually in terms of the binomial distribution. So probability that x is equal to 3 and is exactly equal to 3. And now we're going to go ahead and we're going to type this in. So we want number of trials is 10, probability is 0.5, and the x value is 3. So let's go ahead and hit enter. There's the number that we got. It matches completely with what we actually had right here. We already calculated it, but it's 0.11, and we'll run to 4 places on this, 72. There's our answer. Okay, that's the probability. And we didn't have to create this distribution. We can now just answer these questions using our calculator. Let's continue with this concept. Let's make it a cumulative. So 2. Getting at least, let's say, let's say at least, we'll say 3 heads. Okay, so how that would normally look, if we go back up, imagine doing that here, at least 3 heads. Well, that's where we have to count and add up all these parts, and we would really just say 3 or more. We would add these together. It'd be 5 on that one. But on this one, it's everything from 3 over, and we just add it up. But we can make this go faster where we don't actually have to find all of these. The calculator knows how to do that for us. So we're going to go back in here. We need, so let's press menu 5. Go find the, we want, when it says at least, we want binomial CDF, and we need number of trials, probability of success, lower bound and upper bound. Okay, so let's write out these parts. So in P, we have 10 trials, and by the way, let's write this up in symbols. P, probability that x is, so it says at least 3. So how do we write that? How do we write that? Well, can 3 be an option for us? Yes. So we have a greater than or equal to, so it's got to be 3 or greater is what we want. And this is what confuses students the most in this chapter, is understanding the inequality, or the symbol of less than, greater than, equal to, less than, equal to, because that's what you're going to be seeing in here. And that's why we wrote this. It's a range of values, less than, more than, at most, at least. You have to make sure you're able to distinguish between which ones you're using, okay? So we want to find that probability. We could find it by adding from 3 all the way to 10. We're not going to do that. We're just going to use the calculation for this. The probability is 0.5, and we have the lower and upper. By the way, if you're using a TI-80 on this, it is much more complicated, much more. That's why this is kind of the sole reason that I use the Inspire, because it does make this process a lot easier. So let's go ahead and type in the number of trials and the probability of success, but what's our lower boundary? What's the lowest number of successes we want? Well, 3 is that lowest number, right? And then the upper boundary is we can have the max, which is 10, so 3 to 10, okay? So we're gonna hit okay. And look at that, it's 0.945313. So that's a pretty good probability that you're gonna get at least 3 heads, right? 3 or more is another way to say that. So it's, we'll do that to 4 places, 0.9453. There it is, okay, there it is. So I'm already 35 minutes in here. I want to pull up the problem set and work a problem there for you. We'll have to do a little bit more with binomial, but I think I've gone long enough today for this. All right, so let's try number 36 and number 37. And then we still have to talk about expected value for these. We'll get that in the final lesson for binomial. But let's go ahead and look at number 36. It says a worn out bottling machine does not properly apply caps to 5% of the bottles it fills. We're using this scenario up here. It says if you randomly select 20 bottles from those produced by this machine, what is the approximate probability that exactly 2 caps have been improperly applied? Okay, so it's either going to apply the cap or it's not. So we have a binary situation. If we were to draw out the tree diagram for this, it would have 2 to the 20 outcomes. So we would never want to draw that out. There's a million combinations here. We don't want to do that at all, okay? But a million possibilities for these 20 bottles, different combinations of applying it correctly or not within the 20, okay? So that's pretty powerful if you think about the abilities of these calculations. So we want to know, let's call X, I'm going to draw on this. If I can do it, what in the world? Hold on one second. All right, I had to just paste it in. So we are going to be using the binomial calculator equation to do this, okay? So we're going to use, we need to write this up in terms. So we're going to say X is the number, let me type it out just because it's faster. Number of caps improperly applied. And I spelled that correctly, it looks like. Improperly applied. That's important. So we have to define success right away, okay? Because we need, we're trying to find this. What's the probability that X equals 2, right? That's what we want to know. So we have to, this is a PDF, so we want menu 5, 5, and if you're trying to find the fastest way to get to it, it's 5, 5D for that one. So what is the number of trials? Well, we have 20 bottles that we're looking at. What's the probability of success? Okay, well, it does not properly, so it's improperly applied to 5%, so we want 0.05. Sometimes questions can trick you with this, and the probability of success could be the complement of that, okay? We'll definitely do some practice with those. Next, we want the number of successes. Well, we want K to equal 2. Or here it shows X. So we're going to do 20, 0.05, and 2. All right. So there is an 0.188677% chance, and that rounds up to 0.19. So it looks like B is going to be the best choice. Okay, then we have this next one. If you randomly select 20 bottles from those produced by this machine, what is the approximate probability between 2 and 6? So we have a range here. So you want from 2 to 6. Inclusive means we're including that 2 and 6. have been improperly applied. So here we have a range. So we're going to do n is 20. And let's go ahead and write this up. P that x is going to be greater than or equal to, since it's inclusive, 2, less than or equal to 6. We want to know that probability. Probability that it is not applied properly is 0.05. Our lower and upper, remember that's how we're doing that with the inspire. Lower is 2, upper is 6. So let's go ahead and look at that menu. 5, scroll down to, we don't want PDF this time actually, we want CDF because it's a range. I don't want geometric. CDF. Okay. Number of trials, 20. Probability of success, 0.05. Lower boundary is 2, upper boundary is 6. Hit OK. And we get 0.2641. It's going to round to B. So that's how those are what the questions are going to end up looking like. We're going to get plenty of practice before we get assessed over it. But hopefully this is starting to make a little more sense, these binomial distributions. We're going to have a third lesson over binomial distributions because I definitely want to talk about these questions right here. We had that formula, but we need to talk about these a little bit. And then we also need to talk about expected values, means, and standard deviations of these. But we'll go ahead and stop the lesson there.